Deciding on the Nash arbitration point depends on how we choose the status quo point, like what we decide that the natural game state is before we start working. In the calculus example, I chose an easy point to work with. However, there's a question as what we should use. What about the game equilibrium? It is the saddle point solution, but what about the security levels? Security levels are sort of defensive strategies. What can we do? Well, John Nash decided that we're not taking everything into account, right? If you recall from the geometry of the game, the original, I'm sorry, the Nash equilibrium strongly favored rows, security levels even more so, but that means that Colin has some threats he can play. So the arbitrated solution should include both the initial advantage that Rose has plus the possible advantage that Colin can get when he starts using his threats, possible threats as leverage. So Nash calculated an optimal threat matrix by simply taking the difference of the x and y values. So you take 4 minus 20 to get the negative 16, and 6 minus a negative 2 will give you 8. So there's a couple examples, and you can see how the optimal threat matrix works. Now, who's the maximizing player? So it turns out that a strongly negative outcome means that this is a place where Colin can threaten, right? Rose's value is much, much less than Colin's, so Colin loves playing A, Rose not so much. Well, look at something that's strongly positive. When it's strongly positive, that's a threat for Rose, right? Rose can do okay at 6 and really hurt Colin. So positive values in the optimal threat matrix are beneficial to Rose, whereas negative values in the threat matrix are beneficial to Colin. So now we have a standard zero-sum game where Rose is the maximizing player. And jumping back here, I'll just show you that there is dominance. Rose is the maximizing player, so she never, ever wants a piece of strategy A. So that's why we're solving. It's a zero-sum game, so we're getting rid of the dominance, and we're solving this 2x2 subgame. It does not have a pure strategy solution. And so we're looking at the oddments. Rose's oddments are 8 and 21, 8 and 13. 2 minus a negative 11 is 13. 0 minus 8 is negative 8, so those absolute values are 13 and 8. That's where Rose strategy mixture is coming from. And Colin, we're taking 2 minus 0 to get 2, and negative 11 minus 8 to get negative 19. So that's where Colin's strategy mixture is coming from. But we don't solve for the value of the game in the threat matrix. What we do is we say, okay, well, if Rose would play this under her as her optimal threat, and Colin would play this as his optimal threat, we're going to go back to the original game. And we're going to calculate what these strategies would do against each other in the original game. So remember, Rose is going to play B 8/21 of the time and C 13/21 of the time. So her value in the original game will be her value for playing B times 8/21 plus her value for playing C times the 13/21. So we're going to have a weighted average of her outcomes. And you can see that here, that when she's playing B, she's getting a 10 and a negative 1. How often is she getting that? Well, she's getting that according to how often that Colin plays A and Colin plays B. That's her expected value for B. And then her expected value for C is the same, right? These are Colin's proportions, and these are her values, the 0 and the 6. So now we've got to remember she's going to play this 8/21 of the time. So if she plays it 21 times, 8 of those times she'll get the 188 over 21. and she's going to play rows C 13/21. So again, if she plays this 21 times, she'll get 8 of these and 13 of these. So we're going to take this weighted average, right? So we're taking Rose's, she plays B 8/21 of the time, and when she does, she gets this value. And 13/21 of the time, she gets this value. So calculating that weighted average, we find out she gets a little less than 3.5. Now remember, she got 5.6 as her Nash equilibrium and as her security level. So Colin has a strong ability to threaten Rose. Let's do the same calculations for Colin. So Colin, this is just the expected value of A with him getting 20 and 8 and 0 in the right proportions, right? Rose never plays strategy A. She plays this one 8/21 of the time and 13/21. So that's where this calculation comes from. And Colin B, same way. So remember, he's earning Colin A, he's earning that 19/21 of the time, and then 2/21 of the time he's earning B. So that's where this comes from. And it turns out to be right at 3. So remember, Colin's security level was 0, and his Nash arbitration point was 4. So Rose doesn't have as much ability to hurt him. Let's take a look at the geometry, right? So remember, Rose does a lot better with both the Nash equilibrium and the security levels. And let's take a look at this optimal threat point, right? So at 3.76 and 3, so notice that Colin has a lot of places where he can threaten Rose, right? Rose doesn't want to be back in this area of the payoff polygon. And and yeah, Colin doesn't want to be down here, but look, his security level is down there. He's already down there. So Rose doesn't have nearly as much opportunity to threaten Colin, and she's only reduced his payoff by 1, whereas he's reduced hers by almost 2. So he has a bigger ability to threaten. So this is the way that John Nash was able to include both the initial advantage, right? Rose still had an initial advantage that should be taken account in the Nash arbitrated solution. Also, Colin has a better ability to threaten, which should impact how the solution is formed. So you definitely want to look at the first 5 or 6 homework problems and understand how to do these and what the difference is when you use an equilibrium or a security level or a threat level as your status quo point for the start of your calculus optimization problem. That brings together, that brings to an end the Nash arbitration scheme presentation. Thanks for listening. Have a great day.